The chemical reaction in question is 2A plus B, C plus D. The objective is to determine how the initial concentrations of A and B affect the reaction rate. To investigate this, 2 experiments were conducted with different initial concentrations of A and B. The provided graph shows the change in the concentration of A over time for these experiments. CAR graph data analysis. The graph includes 2 curves, each representing a different initial concentration of B. 1. Experiment with B equals 1.0 rho minus. This curve shows the decrease in the concentration of A over time when the initial concentration of B is 1.0 mem. 2. Experiment with B equals 2.0 mem. This curve shows a faster decrease in the concentration of A over time when the initial concentration of B is 2.0 mem. From these observations, we can deduce that a higher initial concentration of B, 2.0 mm, leads to a faster decrease in the concentration of A, indicating a higher reaction rate. Therefore, the concentration of B significantly affects the reaction rate. Evaluating each option. Option A, when B is 2.00 m, the reaction rate for A is 2 mechas per second. To verify this, we calculate the reaction rate from the graph using the slope of the curve for B equals 2.00 m. Reaction rate equals phi delta T equals minus frac 0.05, 0.025, ecopsisac. This calculation shows that the reaction rate is indeed 2 mech per second when the concentration of B is 2.00 mem. Therefore, option A is correct. Option B, the rate law for the reaction is R equals KB. When we increase the concentration of B from 1.0 mem to 2.0 m, the reaction rate doubles. This suggests that the reaction rate is directly proportional to the concentration of B. Hence, the rate law can be expressed as R equals KB. This direct proportionality confirms that option B is correct. Option C, the overall reaction is second order. To determine the order of the reaction, we need to see how the concentration of each reactant affects the reaction rate. From the graph, it is clear that changes in the concentration of A do not change the slope of the curve, indicating that A's concentration does not affect the reaction rate. Therefore, the reaction rate depends solely on the concentration of B, making it a first-order reaction with respect to B. Consequently, the overall reaction cannot be second order. Thus, option C is incorrect. Option D, the rate constant K can be calculated as 1s minus 1. To calculate the rate constant, we use data from the experiment where B equals 1.0 mems. The reaction rate for A is minus frac delta A, delta T equals minus frac 0.05 minus 0, 0.05 equals 1. Text members equals KB. Given that B equals 1.0 m, we solve for K. K equals frac 1 text m's per sec. 1.00 equals 1. Text s squared minus 1. This calculation shows that the rate constant K is 1s squared minus 1, making option D correct. Using the rate law, R equals KB, and knowing that K equals 1s1, we calculate the reaction rate when B equals 0.1 ample. R equals K, B equals 1.1, A equals 0.1 rho. Text. This confirms that the reaction rate is 0.1 mol per second when B is 0.1 m. Therefore, this option is correct. Conclusion. Based on the detailed analysis, the correct options are A, correct, B, correct, D, correct, E, correct. Only option C is incorrect because the overall reaction is first order with respect to B, not second order.